now on concepts in material design to facilitate anti-gravity and advanced propulsion concepts, including research into ideas like metamaterials, bismuth, liquid metal compounds, and more. Jeremy, for those who don't know, is very well known for scientific and technology analysis on the Alien Scientist YouTube channel. He's been doing that for more than a decade. He has over 100,000 subscribers. And that is really the largest channel of its kind. He has tons and tons of stuff. The other thing I should mention to everybody attending APEC is if you're seeing this, watching live or you're watching it on YouTube, Jeremy does tons of midweek stuff. He has Mark, he has Jeremiah, he has lots of folks on throughout the week doing streams. So if you're watching this now, again, I believe it's youtube.com/alien scientist. Alienscientist.com is another place. And so I would definitely recommend, you could just Google Alien Scientist YouTube. You could find it there. I would recommend subscribing because he has a lot more there than we're doing just in this conference alone. So take it away, sir.
Yeah, Tim, to add to that, we're going to be expanding that soon and setting up a podcast studio and flying, people here if they're from out of town to interview them live in a kind of a 4K and a high def sound setting, and really get into nuts and bolts on work. And we're also have that in part with Mark at the Falcon Space Lab in New Jersey, where we have a lab to vet and verify and test various equipment and ideas. So bring your gyroscopes down or whatever you are building, and we will we'll examine it and do it justice with high def video and some real in-depth reporting. So without further ado, I will start my presentation.
Can you make it full screen?
Yeah, how do I do that? This is Alt-Enter usually works for that, but Alt-Enter. How do I make this?
Check view on a.
Yeah, let's do view, present. Yeah, Control F5. Here we go. All right, so a little bit about me. I have a bachelor's degree in physics with a minor in math from Bridgewater State University. I went on and off for a number of years, switched my major to business management, then I switched it back to physics, and I eventually graduated in 2012. In the meantime, in between, I did a lot of work in construction and materials. I worked for Foxborough and Invensys doing some chemical engineering and got some end experience in industrial automation and control systems. I been interested mainly in metamaterials and quasi-crystals since about 2004 or so, when I got into researching those types of things and all this type of stuff in general. I'm basically a human resources coordinator, and I meet lots of interesting people, and I connect them and network them together with people I think that they'd work well with. And so I've just been trying to link together the people and identify the sources of good information, the sources of good materials, and good different knowledge and subject matter experts on various things to kind of piece this whole puzzle together about what we should be building. Take my money, love your channel. Since you were on the Timcast, thanks to Dr. Fox 2000 there in the live chat for giving me $10 in the live chat on YouTube. Sorry, I have to call these out, or people will donate more money to us to keep this thing going. So anyways, this is Feynman. He did a presentation called "There's Plenty of Room at the Bottom" back in, I think, the 70s on nanotechnology and the future of building stuff on the small scale and what we need to do. And just to give you a scale, we can zoom in on this ice crystal several hundred times, and I think this is a magnification of, scale of 1 nanometer to, I think this is just a factor of 100. But anyways, we're talking about the building blocks of nature. We all have the same building blocks. Assume that aliens have the same building blocks as we do. Except their periodic table includes all of the other isotopes, like all the heavier elements, not like heavy elements up here, but elements with an extra neutron, which change the isotope number without changing the element number. And we have a particle zoo, of course, in particle physics, the standard model, which is the best we have right now until a better theory comes along. We have up and down quark, charm, strange, top, bottom, this Higgs boson field that kind of like holds everything together and gives it mass. The Z and W bosons, the W has a positive and negative boson. Then we have photons, which is kind of like this electromagnetic force, and then gluons, which hold these nuclei together inside the nucleus. It's a really messy model, as our last presenter explained, and there's a lot of attempts to unify it through geometric unity and other such theories. One of such theory that I looked at was called Phoenix theory, the physics of entanglement networks and information exchanges, by a guy named Ken Griggs, who was studied under Sasha Migdal and Jim Gates, trying to relate string theory. And he related a lot of his research to Louis Kaufman, the mathematician, on knots and knot theory, and trying to come up with a new theory of particle physics based on knots. But regardless of how it all works under the hood, we still have the same kind of building blocks for our universe, to what we have to build with. So these are the isotopes. So like all these elements right here is just this black line right through the middle, and then there's all these isotopes on either side, showing that are stable. That, some of these aren't stable, and the further that you drift off, they just don't even exist. But these are everything we've pretty much mapped out, all the way up to these higher elements, which we're still mapping out. There's something called let's break down the periodic table so we can kind of like understand it a little bit better. We have all these non-metals over here, and non-metals are usually positively charged cations. Anions are negatively charged. So nonmetals are usually negatively charged, and metals are usually positively charged. They're alkaline. That's where they make batteries out of them and stuff. And the matching rules based on opposite sides of this table will base on what kind of things can match with what, and it's just all about filling these outer shells with the Lewis structure. But really, there's some interesting behavior right around here, because there's metals that kind of like are metalloids. They're not, this line right down the middle, like bismuth, silicon, arsenic, tellurium, and actinium. It's kind of like they're metalloids. They're not really metals. They're somewhat in between. And then there's also bismuth, which is kind of an interesting metal we'll get to later. But a lot of these metals have interesting properties, and we're going to go through kind of them. It's not as much as we try to classify them based on, they have similar kinds of properties based on this table of elements, like the families going up and down, and also the periods going left and right. But really, every element is kind of its own little building block, and it's kind of important to understand them they aren't seeing the presentation on that screen, so I have to switch. Hold up. I have to switch my OBS because they're not seeing the presentation on their screen. Hold up. Yes. Hold up a second. So, display capture, I'm going to properties, and we're going to there. Boom. All right, so I fixed it. Sorry, they weren't seeing my screen before. Now they are. All right, so we have a bunch of these building blocks, and it's based on the size of the nucleus, how much mass is inside, and how much charge there is. Kind of gives you this whole Greg Chase just threw $100 in the super chat. Keep up the great work and don't give up. Bio Nerd said can't see the presentation. Also, when can I pre-order my Tic Tac craft? So yeah, this was the presentation so far. I wanted to show some of those slides to the audience out there because they didn't get to see them all. All right, so yeah, this was the Phoenix theory. This was the Higgs boson and all the particle physics. This was our table of building blocks. And that's me with some of my math professors on my graduation day. So metals versus nonmetals. Nonmetals form anions. They're dull, colorless to colorful. They're poor conductors. They're brittle. They have a low melting point, often liquids or gases at room temperature, and not sonorous. Yeah, so a lot of these things are actually gases at, oxygen, nitrogen, chlorine, fluorine, chlorine, and hydrogen and helium, of course. They're all really gases. I think the hydrogen's the smallest. I mean, helium's the smallest atom that there is, and size-wise. But they all have different. They all kind of fit together in different ways based on their size. If you can kind of think of like spheres and sphere packing a little bit, but a little bit different. So these molecules and these atoms, the atoms we have in our periodic table of chemical elements. Combined, and I'm having trouble going through these slides one at a time, to form molecules. And molecules can be left or right-handed. So left and right-handed molecules that are opposites of one another are called enantiomers. And it's based on, chiral symmetry. So they're the same in a mirror as the other one. And then there's chemical isomers, which is just basically they have the same chemical like composition. It's still, C3H 6 H7 F1 or whatever. It's still the same, but it's just a different arrangement of those things. And that's different than a nuclear isomer, which is basically like the isomers has equal N, equal A, and equal Z. So an isotope has the equal Z. We have the same proton number, but we just change the neutron number. Isobars, that's equal A, which is, I believe, and isotones, and then, so there's a whole bunch of different variations of nuclei and ways to change these nuclei around based on energy levels, and there's one that's an isomer that we know of, that the lowest one we know of is actually hafnium tantalum isomer, and that one is the lowest stable one, and it actually switches between hafnium and tantalum. It will go back and forth because the numbers switch around or whatever. They can switch around, so they stay equal, but they interchange in a way. So we have nuclear isomers, vibranium. I mentioned that's kind of like what we mentioned by something that changes. It's actually like transmuting. It's an element that's transmuting stably, but you have to keep it stable by energizing it with gammas. And there might be ways to create more hyper-stable elements by keeping them stable using isomers, but basically combining it with a gamma to keep it stable, because it has these decay chains through that decay into different things. So it changes so it can transmute readily based on those decay chains. But anyways, when we have mixtures of metals, and we have metals and all these metals and solids have melting points, and liquid, where there are things where there are solid, liquid, and gas. We know about phases, and building things, sometimes require, changing phase of certain materials for different applications, mixing metals to form alloys. Metals are separated into two classifications: ferrous and non-ferrous. Ferrous is anything that contains iron, including like steel, and then non-ferrous superalloys, light metals like aluminum, magnesium, beryllium, titanium, cobalt, tantalum, and tungsten. Then there's non-metals, which can be used to make plastics, composites, and ceramics, including what are called refractories, like fire bricks and stuff. And refractory, the word refractory means it refracts light, so it can withstand really high temperatures, like fire brick, and that's where refractory metals get the name refractory metals. And that's a section of these transition metals on the periodic table which have a really high melting point above 2000 Celsius and a really high hardness at room temperature. They're chemically inert and have a relatively high density. Tantalum, for example, is used. A lot of these are used in bone and transplants and like limb transplants, because they don't really cause what's it called? They don't cause inflammation. They don't cause reaction to skin tissue. Your body doesn't reject them. So a lot of those metals are used for that and other things. So these metals are a particular part of the periodic table that are of interest. Titanium, there's a Kroll method for purifying it that they use to make this kind of sponge cake of different purities, and they take off the different pieces. But sponges are an interesting thing because it turns out a lot of different metals can be used to make sponges, and also other things like aerogel is a silica sponge, but it's like silica gel, but the gel's been replaced with air to make aerogel. And these kinds of aerogels and aerosponges, including open cell and porous titanium, they're super interesting to research because they can pass air through them, and you could also possibly electrically charge these surfaces in different layers by printing them of different materials of different conductivity. So there's a lot of research that still needs to be done in these types of materials in aerospace. I think there's a lot of research that's being done, but not all of it's public knowledge yet at this point. But certainly these aero sponges are certainly an area of interest to people who've done Biefeld-Brown effect or any kind of in just in aerodynamics in general, because they can be built to be custom aerodynamic. Tantalum kind of has this interesting structure as well, and again, it's really it has really good response to the human for implants and stuff. There's a mix of 1.6 tantalum to 1 tellurium forms a chalcogenide quasi-crystal, which is a dodecagonal quasi-crystal, a dodecagonal. A phase is, and it's distinguished by the presence of crystallographically forbidden 12-fold rotational symmetry in the diffraction pattern. So this is actually, tantalum can form quasi-crystals. Some of these metals can form quasi-crystals. This is one of the few that form it with a bimetallic alloy. Most of them are actually trimetallic alloys. You need 3 elements to form quasi-crystals. Quasi-crystals are pretty interesting stuff when you research them, because they have a lot of interesting applications. When I started researching these back in 2012, they don't have like a single fault line, so they could be made into really strong or durable materials, although we'll get into other strong durable materials and better ways of doing those a little bit later. What they're really interesting is their hypersymmetry, and that the fact that they have a symmetry on a higher level outside, but on the innate scale you can change individual parts and still maintain this greater symmetry. So they have a lot of application for photonic waveguides, 5D. There's also 5D optical data storage. It's not really quasi-crystals. This is actually a nanostructured glass. I believe it's like quartz. And it's for permanently recording digital data using a femtosecond laser writing process. This is established technology. It's not theoretical. This is real. They've done this. The memory crystal is capable of storing 360 terabytes of data for billions of years. It has a really, really, really stable structure. It's really stable in these crystal structures, and can last really long periods of time, much longer than a floppy disk drive or a magnetic disk, or even a CD. First experimentally demonstrated in 2013. Hitachi and Microsoft have been developing this technology ever since. Quasi-crystals are used. This is an Eric Quinones article from Princeton University. Their researchers built a scale model of a quasi-crystal using a bunch of straws, and the straws were the length of the wavelength of microwave radiation that they shot out of this horn at it, and they noticed that it basically reflected those signals at 90-degree angles with perfect reflection without losing signal quality. So quasi-crystals are certainly an interesting area of research that I think should be pursued further for future spacecraft engineering research. Of course, it's a little bit different than metamaterials, which these C-ring loop resonators that we talked about. What's interesting is that you can place the loops inside of one another to make a series of loops that each correspond to a different wavelength. So you can, this one will be like red spectrum. This is orange, yellow, green, blue, just to give a color code to get an idea of how this can be used to break down wavelengths and frequencies that come incoming into the craft. I'm not going to get into all of this stuff because I'm just going to give an overview of the materials. But again, yeah, they have built these resonator arrays with these split C-ring resonators. We believe there might be ways to do this on a smaller scale. Of course, when you get down to the atomic scale, once you get past a certain threshold, you no longer need the C-ring resonators, because what happens is the atoms themselves, actually, the spins of the atoms themselves actually kind of work for you if you use the right atoms with the right properties. So there's also acoustic metamaterials. Just like the structure of matter can bend light to its will, the structure of matter can bend sound to its will as well. Very interesting stuff. So this is like baffling that they use for soundproofing for recording booths and recording rooms. This is I think they place a microphone inside this pyramid and it can't hear anything outside the pyramid because it dampens and redirects all the sound through the material structure. This is the world's quietest room. It's at a company in Ontario, Canada. I forget the name of the company. It's in my notes. But there we go, notes. Yeah, it's the Ekel Noise Control Technologies. It's called ECKEL, the world's quietest room. There's also acoustic chiral metamaterials, okay, in nature. One of them is a seashell. You ever wonder why you put a seashell to your ear? You can hear all the air currents amplified, so loudly inside the seashell. It's because it's a metamaterial. It's literally a chiral metamaterial, and it works similar to the cochlea inside your inner ear for amplifying noises and sounds, and then into this sort of seashell shape, probably Fibonacci inspired spiral there. But in any case, the chiral metamaterials, there's a company Ron Kita runs called Ferroelectric that's investigating chiral quartz and some of these effects of chiral symmetry and chiral metamaterials. Some very interesting research and definitely something worth checking out for future experiments and spacecraft engineering materials. Then we get into metallic beetles. So we talked about metals and non-metals on that periodic table, but it turns out you can take purely organic compounds, non-metals, and make them look like metals by etching them. And these are etched, biologically, but nature is sort of doing it in this case with these beetles and these skin coatings. But when we look at these different beetles under this SEM image, it looks like a series of dots and dashes, and it's just basically like there's no color or no tonation which makes it look like that. It's just basically the structures and how they interact with light on the skin themselves. It's nothing to do with the composition of the material itself. It's just the fact that it's not exactly metal. It's interacting like a metal because of its structure. So thank you to Infinitum Neo for the $100 super chat. He said, great info. Thank you so much. That's an awesome help, man. This is great. So we have, we find out that if we etch, University of Rochester, a guy named Dr. Chun-Li Guo is doing research into materials, and he found out that if you etch these materials with a laser, do laser etching, micro and nano pitting, similar to these nano pitting on the bugs, but you try different, patterns and different shapes, which we've learned from looking at the bugs. This one makes gold, this one makes this iridescent green and whatnot. They're actually able to engineer materials that are hydrophobic. So these spacings in the microstructures are actually tuned to water molecules specifically, and then they can do it to make them hydrophilic. So phobia means hate, philia means love. So hydrophilic materials are materials that love water, And you see how it goes right to the edge and sticks right to this material. It goes right off this, you know, super hydrophobic material in the middle. Most hydrophobic coatings that exist on the market presently work on chemical deposition of a layer of material that has this effect. When the polymers dry out, it creates a surface very similar to this. This is the no application I know of where they can just laser treat a metal to give it this coating, which is really, really awesome to think about. So, Nosa in the chat says there are better methods for super hydrophobic and super hydrophilic. Yeah, I'd like to check those out, but this one I just thought was cool because it relates to, you know, we can do the same thing. If we laser etch these sort of patterns, we can make it look like this bug, or that gold color, or the green color, or whatever kind of color we want it to look like. And I just thought that was interesting. And then the application for if you take epoxy thin films and then etch each thin film and then apply them in layers that are tuned to different layers, you can make dielectric mirrors, which we'll get into in just a second right down here. But we'll talk about, you know, yeah, so I'll just get right into the dielectric mirrors and then we'll go back. So we have something called Bragg diffraction when when incident, you know, light hits a crystal or a structure. And different frequencies transmute or go into the material at, you know, have different penetration depths, to different have different interactions with every material. So certain frequencies will bounce right off the surface of the material, and some frequencies will penetrate deeper into the material and then bounce around, or sometimes they don't reflect back. But what a Bragg mirror does, or a dielectric mirror does, is it tunes each one of these layers to those next frequencies, so that when they bounce off, all these frequencies sort of bounce back off. And it's very interesting what you can do. So examples of these are called dimensional crystals, and that one would be a 2D, or a 1D crystal. So that would be a 1D. See these layers? So that's called an example of a 1D. You add these wafers and it creates a 1D optical dimensional material. And then if you get a 2D one, would be example of the surface, which is just like this. This is a forest of carbon nanotubes, and that's what Vantablack is. That stuff Vantablack is literally, it's a forest of carbon nanotubes. It's like a carpet of them. And the carpet of these nanotubes, it basically absorbs all the light that interacts with it, you know, or not all of it, but 9% of it, you know, a ton of it. So I think it's like 90-something% of the incident light it absorbs completely. And that's an example of a 2D dimensional crystal or optical metamaterial. And then they have 3D ones, which are more complex, which are those like quasi-crystals and those other structures that we should be building in the future to run all of our electronics off of, because we don't need to push electrons around anymore. We can push photons around, and we can build circuits that work on photonic energies and the alignments of these spins of carefully aligned atoms and molecules along the circuits. Once we are able to build that small and do those kinds of things, and it's all based on waves and waveguides and mirrors and understanding that sort of technology, but on a intricate atomic and scalar lattice level. And that's the level as small as we can go. If we can go that small, we're dealing with, you know, it can't get too much closer to alien technology until we get into the other building blocks. But it's basically chemistry all the way down, regardless of how it works under the hood. In the land of unification field theories, we know a lot about these kinds of materials. So next thing is shape retention alloys that I wanted to mention on here. Shape retention alloys are important because they can deform and like you put it in hot water and it will go back into shape. Like nitinol wire, you can deform it any which way. You throw it into hot water and it goes back into shape. And it deals with these, you know, austenite and martensite phases and how it can deform and go back into phase. And it's interesting because it's just all about how certain molecules and certain types of atoms linked together on this fundamental level. And as we learn more about that, we get to the topic of metallic glass, which is a real anomaly and almost a strange thing that almost shouldn't exist. But we talk about metal structures and the structures of just how things form in general. And things can form in crystals, where if it cools really slowly, it all kind of it forms like a hard crystal, and this is what's called the solid state. Amorphous structures are like solid state, but they have like a 2% elastic limit, which is higher than any kind of metal or any kind of solid material. So they're really, really flexible. They're much more. Wood has an elastic limit of 1, for example, and polymers have elastic limit upwards of 2.7%. So it's right around there. Plus, it's got really high strength. So glass alloys and metallic glasses are really interesting, remarkable materials. I once compared them in a video to the Roswell memory foil that they talked about, that unbreakable like material that you could crinkle it up into a ball and it would unfold itself. Although I haven't seen any material exactly like that, any metallic glasses exactly like that material. It is an interesting material. There's a video on liquid metal tuning forks that you guys can watch. Liquid Metal Technologies is a company that makes these. I don't know why that one didn't load. All right. Oh, this one's important. So this graph shows you imaging and tweezing, and talks about the length of tissues and organs and cells. We can use MEMS and scanning electron microscopes to kind of see on that level. Then we can use optical and magnetic tweezing to kind of move things on that level. And then when we kind of want to see below cells and into proteins and maybe even into atoms themselves, we got to go lower. But we use one of the types of tomography is GPR and ultrasound imaging, which ultrasound uses really high frequency sound waves and takes the bounce back, and they can use it to image things that are inside of like the baby inside of its mother, or also ground penetrating radar to see pipes and other stuff that's buried underneath the ground. It's also very nuclear magnetic resonance imaging. They put you through a giant magnet, and they use this tomography to basically create an image of you in slices, and then add those slices together to get an image of your whole body. And that's kind of like it started. There's a whole thing on tomography if you look it up. I had a whole page on it, but there's a long list of all like the history of the machines and where the technology's gone over the years and the methods and stuff. But what we're getting towards is optical tweezers and all this stuff. What we eventually want to get towards is that the fact that 3D printers will be known as ancient replicators, and we want to build this replicator from Star Wars. There's a couple things about that. We're not quite building a replicator with 3D printing. 3D printing has its limitations. Called additive manufacturing. Certain things are still better to build on a CNC and milling machine, and out of a cast solid piece, because it's a lot stronger than something that's built up of a bunch of stuff that's been printed together. Something that's cast as a whole and then cut and reduced down through reductionist machining is sometimes better, is clearly superior than a lot of these other things. And also, this would be limited to physical objects in your 3D printer. You could. I don't think they'll ever be able to 3D print you a frog or a biological living organism, or even print it something this fast, to come in. So, but who knows? The future may hold amazing things. But in any case, that's kind of what we're building up to. But we got to keep it within the realms of realistics. Composites are fabricating materials that involve mixing a metallic alloy in a solid state with reinforced particles or porous mass, and then infiltrating metallic alloy in the semi-solid state. So you can also mix different alloys with non-metals and stuff. Lots of different, you know, expansion room and inventive ideas for composites, and lots of room for invention there. Carbon is, as we all know, is one of the building blocks that we definitely need to pay attention to. You and me were made out of carbon. We wouldn't be here if it weren't for carbon, DNA, and all our life forms. We love carbon because it forms really long chains, and really long chains are useful for building stuff like DNA and humans and little kittens. So we love carbon. It's also stuff we burn, hydrocarbons. There's a lot of energy in those bonds, so we use it for fuel. And it's currently the biggest fuel source on the planet until one of us invents free energy. So definitely carbon buckyballs. So there's a bunch of different Buckminster fullerenes. There's bucky tubes that can be formed from rolling graphene sheets into tubes. Graphite, of course, can be made into graphene through the Scotch tape method or electrostatic confinement and other methods. But there's also printable, we know that carbon can be made into diamond. That's another isomer or type of, is the diamond shape. So we can arrange, if you pack lots of carbon really close together, you heat it up and you pack it real tight, you can make diamond. There's also printable diamond, this stuff called polyhydridocarbon, which it's called, or PHC. It's a polymer that may be readily fabricated into various forms, like films, fibers, plates, and then thermalized into a final hexagonal diamond ceramic. Upon thermolysis in argon at atmospheric temperature and pressure of 110 degrees Celsius to 1,000 degrees Celsius, decomposition of polyhydridocarbon results in hexagonal diamond or Lonsdaleite. Lonsdaleite, as you know, it's a translucent diamond. It's hard. It's about 58% harder than a diamond, a natural diamond, and it's produced through by a number of companies, synthetic diamonds, in a number of different ways. This is from Genesis Diamonds, and this is Genesis Diamonds Laboratory and their methods for manufacturing diamonds. And the high pressure types of environments that they use for that. Carbon chains, yes, as we know, they're pretty much define three huge realms of chemistry just on carbon alone. So it's very important for chemists. Biological, inorganic chemistry, and organic chemistry are all directly related or linked to carbon and what can be formed with carbon. The other one right under carbon, of course, is another key building block, just where it sits on the periodic table. It's just in the middle, straight down the middle of everything. So it kind of it branches off to everything, if you think about it, where it sits on the periodic table. Same with silicon. Sorry, it'd be important to make this distinction, because it's really easy to say the wrong thing, because silicon is the element. That's what they mine out of the earth. It's the second most abundant element on earth after oxygen. Silica is quartz or glass. It's actually silicon dioxide. It's produced from the reaction between silicon and oxygen. And there's silicone, which is produced from the reaction between silicon, oxygen, carbon, and or hydrogen. And it's a kind of like a gel, or the silica gel is silica. And then, so yeah, it's very confusing, but I think we straightened it out. So high melting point, high boiling point, bluish grain, middle sheen. It's used in semiconductors and computer circuits and other electronics. Of course, if you take silica gel and replace the water with air, it makes aerogel, which is really heat resistant and fire resistant. It's good. Fire block material. It's also got very good compressive strength. Not that it will cut with a knife. It's not, super strong or rigid material, but it will support some weight. And then there's also graphene aerogel, which is just basically like graphene, but in an aerogel form or with lots of gaps or air between. And there's even, 3D printed lattices of this to make it even more even lighter. And there's lots of applications with graphene aerogels currently. Dr. Tianyu Li at Lee's lab in the University of California in Santa Cruz is doing work on 3D printing of three-dimensional graphene aerogels with periodic macropores for supercapacitor electrodes. There's also another number of universities doing experiments with nanoporous graphene membranes and also graphene channels that mimic or replicate the action of biological ion channels, so they can open up or these pores in the surface of these graphene sheets to let different molecules of different sizes through, depending. But in any case, then we have 3D graphene, base sensors and piezoelectric switches. So they have these graphene structures that when they press them together, they create these electrical switches, or also piezoelectric voltage, needles, whatever, pressure sensors, if you will, through piezoelectric action of the graphene, which is also interesting application for the graphene. Is it the wonder material? We've all hailed that it was. I think so. I think that anyone who sort of underscores the virtues of graphene hasn't really done the research, and it's really underfunded right now, as far as I can tell. It's strong, it's thin, it's conductive, it's truly two-dimensional, it's stretchable, and it's multidisciplinary and it has a lot of applications in a lot of different fields. So I just believe we haven't even begun to see the full extent of applications of graphene yet, and it's definitely a technology that we need to consider in our experiments going forward and in the future. Piezoelectricity, of course, it's exhibited in graphene, but we all know it came from quartz originally, or PZT, lead zirconate titanate. Same kind of idea. That's the interesting stuff. When you vibrate quartz or tension and compress quartz, it produces a voltage. And well, yeah, graphene's cool, but there's lots of other stuff out there that we're looking into and stuff, as well as graphene. So that we'll get into it. So let me continue. Ferroelectricity, spontaneous electrical polarization, discovered in 1920 in Rochelle salt by J. Valasek. Okay, so he made this Rochelle salt. This is a large crystal of Rochelle salt that was grown on Skylab. It turns out that if you grow this salt in zero gravity, the crystals that it forms are much more ferroelectric than the normal crystals grown on Earth. And so that is just some of the research that NASA and other organizations have done into crystal growth in space, and a lot of it's based on these materials. The ferroelectric materials led eventually to the discovery of nonlinear optical materials, these multiferroics like barium titanate, which we'll get into in a second. Ferromagnetism, of course, is just a magnet. It has a natural, iron, like natural iron is ferromagnetic. That means it's like a permanent magnet, just naturally. Paramagnetic means it will line up and become a magnet as soon as you put, any kind of a magnetic field on it. So like an iron bar that's not magnetized is paramagnetic. It will become magnetized, but if it's already magnetized, then it's ferromagnetic. And if it doesn't get magnetized at all and it's completely inert, then it's diamagnetic. And then ferroelectricity is kind of like the analog between ferromagnetic and ferroelectric. It means it becomes electrically polarized within a field if you apply a field to it. And these curves right here, see these curves? Those are called hysteresis curves, and we'll get into those in a second. Talk about those because they come into play. The transistor, diodes, and solid state physics goes back to Walter Schottky and also those guys at Bell Labs who invented the transistor. They were doing a lot of the theory on solid state physics and group theory, and essentially the core physics into how to build these kinds of materials that were used to build the first transistor. That did not come from aliens, as Philip Corso says. It definitely came from human scientists working on it for decades before that, and it was all it's all there. So cold fusion is kind of related to these metal halide lattices. I had to throw this in somewhere, so I threw it in here. I apologize for that, but metal hydride lattices like palladium, in cold fusion experiments, they put heavy water plus an electrolyte, and then they charge this cathode, a palladium cathode, and there's a saturation point of about 94% deuterium to palladium that you need in order to see the reaction, according to Mitchell Schwartz and the MIT guys like Peter Hagelstein. Mitchell Schwartz was the experimentalist doing the research on cold fusion at MIT, who I talked to, and came up with this along with several other scientists who have working in the field, who have kind of agreed that MIT replications were down here around 0.86, 0.88, where they've gotten no results. And so they didn't get their loading ratios high enough within their crystal lattices to achieve what we've reported, or what numerous scientists have reported as fusion actually taking place in the lattice structure of these cells. There's physics that can explain this. There's a new theory out there there's several theories out there with physics that explain kind of how these reactions can take place within metal lattices based on lattice effects, and also like vibrations and Bremsstrahlung radiation, Cherkanov radiation, and other ways of sharing sharing an excitation across a lattice. And so that's what allegedly takes care of the gammas in these experiments. Interesting stuff. But again, that might have some relation to, again, it's not really it's not really apparent how we can use cold fusion to get energy technology out of it yet. But I'm sure that through material science and maybe some of these experiments, we'll be able to direct that energy and those lattice vibrations from cold fusion, and maybe make some sort of device that can actually utilize that energy instead of losing it all to a lattice. But in any case, more work needs to be done in that field, and more research, I believe, because our spacecraft is, of course, going to need an energy source, and pound for pound, cold fusion is a real good bet for fuel source being abundant in water, and the energy output that we get from it. So, in any case, we're going to talk about perovskites and high efficiency photovoltaics. So it turns out that certain types of materials work really good as photovoltaic materials, and those metal halides tend to work really good, but perovskites are probably one of the best. And they're used to make, bismuth ferrite is currently used to make some pretty heavy duty solar panel material and solar cell material. But through material science and construction of lattices, we might be able to effectively make this kind of stuff even better. And we'll talk about that in a second. Bismuth, the most diamagnetic element, it has the highest, it's basically the spinniest, has the highest spin. Nuclear spins and magnetic resonance, this kind of where the material world meets the quantum world. It's an interesting realm to play around with, and I think that as we're learning with some of our research into Alzafon, who I mention here in a second, it's definitely something that the aerospace companies and the government and military have looked at as far as a source, understanding atomic spins and atomic spin orbits of these materials. It's definitely has something to do with it. We've investigated a material called spin glass, another one that it's basically like a glass, but you are injecting these atoms into the surface of this material, which have these aligned spins or predestined spins, or even materials which line up to the spins readily. And so that you could basically create like local magnetic monopoles. Even though it won't be a real magnetic monopole, you could almost create local ones on the surface of the craft through these, really, strange electromagnetic effects which would appear on the surface of these craft if you could coat them with spin glass. And these spin and advanced optical glasses, it's basically like you're condensing light and matter, but also there's you create what's called a Fermi liquid. And Fermi liquids are quite interesting. It's similar to a Fermi gas. It hits this this sort of critical point with temperature and pressure, where along this curve right here, it stays classically critical. And this is all in Landau's Fermi liquid theory, which you can look up. But it's basically a whole new state of matter that is yet to be explored. It's very cutting edge and new, and it might be some interesting things to explore in there. Mercury is another interesting thing. Of course, it's very dangerous. We mentioned about doing some experiments with Mercury earlier, and there are a number of groups out there currently looking into do some experiments with Mercury. We've all heard of this nuclear-powered flying triangle that Ed Fouché talked about in 1998. Although maybe some of you haven't yet, but he was the guy that came out at IUFOC in '98 and talked about this flying triangle craft that spun mercury plasma doped with a bunch of other earth elements and whatnot. And he also talked about quasi-crystals and metamaterials, which were really before a lot of the research was being done publicly into metamaterials or quasi-crystals. It's really hard to find references to any of that stuff pre-1998. But he's a guy that worked at all the right places to have been out at Area 51 back in the early 80s, late 70s, and seen some stuff. And he's certainly an interesting guy, even if he doesn't have a lot of evidence to back up his stories. It's unfortunate. That's sometimes what we have to work off of. Of course, doing some research into rotating Mercury, spin gravity research, we came across a guy named Henry William Wallace from Valley Forge, Pennsylvania, who was a General Electric employee, and apparently he had said some of these ideas about his anti-gravity thing with rotating Mercury to some friends of his at work, and he had he actually patented an idea on it. And it turns out that the military was also, doing research into it and had built his patent, and were researching his same idea for this kinematic effect or gravitomagnetic field. And, we had talked about this tokamak reactors being repurposed for some of these experiments on plasma currents. And because plasma is it's like the fourth state. It's the fourth state of matter above a gas. So you have an extra degree of freedom, and there's been a lot of research into what plasmas can do and different types of plasmas. And you mentioned red mercury as being, I think, who was that? Evan? Was that Ronald? Who mentioned that? Sorry, I forget who it was earlier that mentioned it was barium titanate in the red mercury, but it might be other things. It could be also a liquid alloy of mercury, ammonia.
That was Paul Murad.
Yeah, that was Paul. Paul Murad said that red mercury was barium was mixing some barium titanate in with the mercury. We might have some interesting effects.
Also, plasmas have some plasmas are near superconductors.
Interesting. Yeah. So this again, this ferroelectric hysteresis curve of where you can pump energy into the electric field and the polarization. There's a paper from 1966 on superconductors and gravitational drag by Bryce DeWitt, which is also interesting, showing that some of the theoretical work that was being done as early as 1966 into superconductors or rotating plasmas and gravitational drag, and trying to understand gravitational drag and in terms of these really large weight rotating, it's kind of like your flywheels that you guys were building, but a really, really huge flywheel, So I believe this was related to Boeing's Alzaphan anti-gravity study of 1981 with rotating nuclei and nuclear orientation as a concept for affecting gravity. NASA had a gravity probe B. They were experimenting with the frame dragging effect of this satellite as it went around the Earth. And apparently their results were positive. There is frame dragging. There is an effect. So it's quite possible that if you have your atoms aligned as little gyroscopes, there could be some kind of a similar frame dragging effect or gravitational effect. So that's an area for investigation with materials as well, which is why I included it. The next is barium titanate crystals. Barium titanate, super interesting. Barium titanate was actually discovered where they were doing a lot of research into the ferroelectrics and ferroelectric materials, super ferroelectric materials like barium titanate. So it becomes a photorefractive effect. So the photorefractive effect is a nonlinear optical effect, and it's seen in certain crystals and other materials that respond to light by altering their refractive index. So this material actually alters the refractive index of light. The effect can be used to store temporary erasable holograms and is useful for holographic data storage. It can also be used to create a phase conjugate mirror or an optical spatial soliton. These are all really important, key things if we were to understand light, gravity as a field of the electromagnetic field, as a part of the electromagnetic field. Because these nonlinear optical materials will teach us ways to kind of trick light and possibly ways to trick gravity if gravity behaves anyway similar to light or on frequencies that can be operated by, say it's all light frequencies at once. If we understand, some of these concepts combined, we might be able to build things that can, break optical gravity by recreating the spatial holograms. If gravity is kind of like a hologram, we can recreate a spatial hologram for the craft and kind of break gravity using these spatial holograms via these phase conjugate mirrors, which are really interesting materials. It's like a mirror that, wherever you turn it, no matter which way you turn it, you're always seeing your reflection on the mirror. It's always, you're always bouncing it back to you. You're always looking at yourself. And they're used in this experiment right here on phase conjugate mirrors. I want to play this video. I'm going to go find this video and play it real quick.
Isn't the phase conjugate mirrors what Apollo left on the moon for detecting the distance to the moon? That
was a little different. That was actually it was a special kind of a mirror array, and it was I'm not sure if it was a phase conjugate mirror. I'll have to look into that, Mark. I'm not exactly sure. It might be. You might be right. I'll have to look into that.
I think it was it was an array of mirrors at 90 degrees, so it made that effect. The light would bounce up from one mirror to another. No matter which angle you came at it would shoot right back to you. Two right angles.
Yeah, that makes sense. It probably was. It would be easier to target it that way. If it was phase conjugate, yeah, because then they could target it much easier. They probably did make it like that. But yeah, it just goes to show you, little things like that we're not told to the public. They're just yeah, it's just a mirror up there. But they wouldn't give you these little details. A lot of these details were classified for many, many years as this research was being done. So it's good that this is all coming out to the public now about this. So this is optical technology. They show this the hologram of the face. I forget who the guy is in the hologram. I think it's Max Planck or something. But so they find the focal point, and that's where they put the beam splitter, right at that focal point. So this mirror is reflecting this. It goes this way, and then it reflects back. So now it's not reflecting anymore. With this, they put this cup over it. It breaks up the beam and messes it up. It's because it's got frosted glass. And then they take this conjugate mirror, and see that they twisted it, and they twist it till it goes into phase, and it has to, like, it goes into resonance. And phase conjugate mirrors only work at resonance, so that phase conjugate mirror is tuned to that laser frequency. And you see how that happened. It tuned rather quickly. It didn't come instantly. That mirror didn't reflect the image instantly. It sort of, it resolved it slowly. You see that, how it came? It didn't come on in instantly. It kind of, like, it took a second to resolve the image, because it's literally doing optical calculations, which is why I was like, you know, I suggested that, you know, Jack Sarfati in our other lecture, that his a lot of these calculations that he's talking about could be done optically with the right optical materials, and this is what I'm talking about. So this forms a diffraction, and all this, it breaks up all the light going across there, so it all bounces all these different directions. Now that mirror literally has to find back all those paths through the glass to find the exact paths back, but it eventually resolves them all through optical computation, and the image comes into resonance and resolution on the screen. So if we can think of gravity as an imaging, you know, an imaging technology, or an optical imaging technology, using the right kind of phase conjugate mirrors, which again, this phase conjugate mirrors are tuned to that frequency of light. So if we can build phase conjugate mirrors which are tuned to the frequency of gravity, we could potentially trick gravity into the illusion of or hologram of that it's in a different spot. And one way to potentially do that is through what's called four-wave mixing. Interaction between three wavelengths produces this fourth wavelength, and then you could use that fourth wavelength as a pump beam. So it might be possible to resonate at the frequency of gravity using, you know, phase conjugate mirror materials applied to a surface of our craft in the right way, and in conjunction with four-wave mixing, so that we could, you know, use that to bend the local fabric of space-time as we're trying to do with these skin coatings and skin structures. So ideas were a couple different things that I wanted to mention as far as chemistry goes, and with the types of chemistry and physics that we need to be looking into. I believe are plasmon polaritons, phonon polaritons, which are vibrational lattice, you know, vibrations, polaritons. Then there's exciton polaritons, which are excited states within the material. Then the Cooper pair polaritons, which are like those like magic angle graphene and some of those other types of materials where you line up these states to create these Cooper pairing, and in superconductors, even in superconductors you have sort of Cooper pairing, and there's a lot of interesting things you can find on polariton condensates with superconductors. Of course, closing the terahertz gap is going to be a key thing for our electronics and merging our light with photonics. But these exciton polaritons and polariton chemistry, there's a channel I found on YouTube called Polariton Chemistry Webinars, and they're doing a real good job of teaching some of this stuff, much better than I am. But I'll have to refer you to their videos. But we have nanoplasmonics, which is these polaritons, which are basically like a material waveguide that traps light. So light goes into a material and gets trapped in a material, and then if you pump this material with enough light, it builds up really heavily, and you can create negative mass. Here's an article on negative mass and a new way to create lasers at University of Rochester using these pumped polariton states. And these a lot of these sandwich materials are being investigated. Graphene sandwiches, and graphene layer sandwich between two other materials, or two graphene layers of bread with a superconductor in between. There's been room temperature superfluidity in a polariton condensate reported, and room temperature exciton polariton condensate and lattice. So it's a very easy way to do condensed matter and condensed light coupling. It's it's much easier than creating Bose-Einstein condensates or a lot of these other kinds of more exotic matter states that have been done in laboratories. It's easier if we create these sort of layered sheets and these layered materials the right way. See, these are the graphene sandwiches I'm talking about. This one has a superconductor in between. This one has I forget what they had in that one. This one's got calcium atoms and stuff, but they're basically a whole bunch of stuff that you can find on 2D layers of graphene with various materials sandwiched in between. And twisted bilayer graphene is also a thing. When you get to a magic angle, it becomes suddenly superconductive along one axis, which is super interesting. Learning intricate things about how to exploit quantum mechanics using materials. I wanted to talk about, I mentioned David Perez in this. He's building a spacecraft with this technology he's testing, and he's using. You zoom in really close on his circuit boards. These are snowflake. These are like Koch snowflakes. And there's a guy named David Cohen, Nathan Cohen, I believe, Nathan Cohen, and he runs fractal antenna systems where he builds. He takes these like Koch snowflake patterns and does like numerous iterations on them, and finds that when he builds these antennas based on fractal patterns, they tune in, they become metamaterials basically, and they become super resonant. And I guess this is what he's trying to do with this. Although, you could, I suppose you could do this a lot better. You could do a lot better than this. We could do a lot better than this, and we should be doing a lot better than this. Another thing worth mentioning are flying donut pulses. Schematics for, they're also called spatiotemporal optical vortices. So if you want to look up, sometimes they change the terminology on these things to obscure them and so make them harder to find. But this is a schematic of a metamaterial generator of flying donut pulses. Concentric rings of azimuthally oriented linear dipole resonators with spatially and frequency dependent scattering properties led to the emission of a toroid single cycle flying donut pulse. The resonator in different rings exhibit a different frequency dispersion. See the inset, and so the temporal and frequency form of the single cycle radially. Sorry, I can't read the rest because this thing's in my way. But in any case, oh god, and there it goes back as soon as I try to exit. All right, never mind. No, that's not what I wanted. All right. Hold up. I'm trying to present. Okay. And now I'm way up here for some reason. Hey, man, it skipped a bunch of slides, I swear. Let me just make sure I didn't miss any as I go back down through this list. Oh, come on. I'm not using that mouse wheel. That mouse wheel's cursed. All right. So materials engineering, optical materials, and now we're getting down into these layered types of two-dimensional materials, also two-dimensional waveform materials, shaping their materials like waveforms. Then these really interesting flying magnetic donut pulses things, which are kind of an anomaly in physics. And then also holographic Higgs scalar light matter coupling. There's some interesting papers on light scalars in composite Higgs models, and also light matter coupling with the Higgs boson and Higgs mechanism, which is the gravity field itself. So when we talk about light matter coupling, we're talking about trapping light inside of these metamaterials, producing polaritons, and then what are also called time crystals. So this is kind of relates to the those amorphous metals in the metallic glass and these sort of bendy resonant structures, and the idea that our UFOs are shaped like a bell or a saucer, or a cymbal for a drum set, you know. So this symmetry and this sort of metal shape is ideal, I believe, for creating, you know, matter resonances. And when you have matter that's oscillating or resonating in time, and then you have that matched to a light coupling with these two light waves canceling to create a scalar light field in conjunction at the same frequency of your vibrating surface of the craft, you could produce what are called time crystals. And time crystals could be used to create, you know, basically, you know, gravity, warp drive. And this might be kind of, you know, where we're going in the future with these nano coatings and these nano technologies and stuff. And I had that as the last bit of my presentation, but I will end it with a quick jump over to Battel's website, who just got. And Battel was just awarded this $46.3 million contract to support manufacturing of materials for extreme hypersonic environments. So these are the skin coatings for these Mach 5 Plus craft that they're admittedly developing, although, you know, I think it goes a little bit beyond that, especially with, you should realize it goes a little bit beyond that with some of the stuff that we covered in today's presentation on materials. And I hope there was, I'm sure there's lots of stuff that I missed, and let's bring that up and let's get some comments and questions and discussion on some of these ideas and some of these things.
Okay, well, Jeremy, it's Tim. Let me jump in real quick. So first thing, and again, we owe you an applause. I'm going to put it on gallery. Oops. So you know what? Let me, here, I'm going to stop your share. Yeah, there we go. And everyone, this has been tremendous. Over 100 slides. So amazing, amazing. Jeremy Reese, the alien scientist himself with one of the biggest channels, and he's presenting at our conference today. Thank you, sir. You know, I was taking notes that whole thing, actually. I wasn't familiar with a ton of that stuff. So wonderful. I will definitely be coming back to that when we get it up on YouTube. So let us go to questions now. And here, I will put it back on speaker view. Jeremy, you were unmuted. And let me see, who wants to go first? Okay, so let me see. I have a bunch of references about coffee. Let me see. Mark and Jeremiah are both slugging coffee.
I think Ron Keto over here is trying to get your attention.
Oh, is he? Sorry, I can't see all of those. There's Ron. Ron, go for it, sir.
Okay, hold on. Am I there? Am I here? What I'm going to do, I got so much stuff. Fantastic presentation, best ever, 5-star by Jeremy. And I'll make it short. I'm going to put it in an email because what I'm going to cover, I'm not sure if he was aware of the super heterodyne periodic table of Walter Russell. I'm not sure if that is in anybody's coverage. The Walter
right.
Russell
So we talked about this whole linear shape of all this materials, right? And then I got into the chiral stuff and I showed how it could all be rotated in the spiral. Well, that's what Russell did with the periodic table. He said, "Oh, it doesn't go like this flat table. It's actually a spiral." I thought that was brilliant. Yes, I have seen that.
Because what it is in terms of insight, if you want to get an insight in terms of being predictive and things that people don't even know about. Walter Russell was not a scientist, he was a seer. And in my life, what I've learned from is you don't go to a theorist, you go to a seer who knows something, they don't have any way of knowing it. But what I'll do in a letter, email to you, I did reverse patent citations for Wallace. Henry Wallace, in his patent, you'll see he lived in Ardmore. When he lived in Ardmore, I was at Villanova, and the government was watching his stuff, and I threw reverse patent citations on Dialogue Information Services back in the 80s. I tracked it back to China Lake. The next one was, oh God, I'll just a short item here. I'm trying to get through this. Elon Musk, I was linked in with Elon Musk for 2 weeks, and then he realized I was anti-rocket. But last year, Elon Musk, I thought it was SpaceX Corporation. Are you familiar with Maxwell Laboratories? Maxwell Laboratories? Maxwell Laboratories is known for supercapacitors. And I heard that SpaceX was acquiring Maxwell Labs, but in the press announcement, they have it that Tesla Motors is acquiring for supercapacitors. But I always thought electrogravitics and Maxwell Laboratories is a match. I got two more items here. Ron Burgoyne has a patent on bismuth superconductors. I'll send that to you. And then a lot of times when I see NLO materials, are you familiar with second harmonic generators? A second harmonic generator will take a light signal in and double it. It's a doubler. NLOs and SHGs are related. I was trying to talk to a Penn professor about it, and in terms of him giving me the shaggy dog story, and that's it. Oh, before I go, if people want to experiment with pyrolytic graphite sheets, you can buy it. It's called pyrolytic graphite sheet. It's used for levitation experiments with magnets. And the other one was, I think that covers it. I got it covered here. That's it. I'll put it all in an email. And chiral materials, due to their structures, are usually intrinsic piezoelectric. And the final item is that on one of your diagrams, you have an imprint of a Mercury donut with electrodes. If you want to spin Mercury, that's a good way of doing it. Just add a magnetic field. That's it. Okay, I'll be in an email. Hey, thanks again for a super presentation.
Ron, thank you, sir. I'm going to meet you out now.
We have over 200 people watching live right now. Just so you know, this is even more than was on earlier.
So who has more questions now? Who wants to go next? Jeremy, you blew my mind, man. I think you blew everybody's mind. I think that's why it's so quiet. I think that it's just kind of this dull rattling sound in our heads while we try and fit all these pieces together. So
I'm sorry if I rambled and skipped over a lot of stuff because it was like awesome. Trying to fit it all in because I had a lot of slides and it was just over an hour. So that's what I was aiming for.
You know what interests me is this. I hear the word metamaterials over and over again. I'm sure that you have as well, right? In these email lists. And it's almost like a buzzword that gets thrown out. Anytime you need a magical property, you use metamaterials. And so actually for the first time, really ever in this community, you're actually laying out what is a metamaterial, right? And you actually didn't go too in deep. I mean, it goes even deeper than that, but you did do this enormous, massive overview of all these new structures and properties of matter, you know? So that's amazing. Structures
are key because all matter is structures, and all it's built of is structures, and the structures are super important because there's symmetry in those structures do different things. And like I said, giving examples is the key way, because I didn't have to, I gave people a real good idea of what metamaterials are with, a seashell is an acoustic metamaterial because it's chiral. It's chiral though, because of the shape of the inner chamber inside there. And that's, I don't know, it gives people something more to like, oh, that's a metamaterial. Now I can kind of understand this a little bit, what people mean by metamaterial. It's these unique properties that arise because you're literally, because of the structures of that shell, you're literally lining up all those waves in a way that it allows for complete transmission without any signal loss, essentially. Same idea. So yeah, it's
sorry about that, Jeremy. I just accidentally muted you. I was trying to unmute myself. So Wayne Ojala, Wayne, sir, let me ask you to unmute. Jeremy, you probably need to unmute yourself as well again.
Yep.
If Wayne is there.
Don't forget to like and subscribe to the channel, everyone watching live. Thank you to Dr. Fox 2000 for the $5 super chat.
Sorry, Wayne just said that he can't unmute himself. He's saying, Jeremy, can you explain trap light And does trapped light encompass all wavelengths of EM?
All right, so I can speak to that. I don't know if it encompasses all wavelengths of EM. There is that, of course, it would exclude that terahertz gap we're still trying to fill and build materials that will interact on those frequencies and wavelengths. So, but yes, trapped light, there's a researcher named Len Howe, I believe, at Harvard. Let me just see if I'm spelling this right. Lenhau. Lean Howe. Okay, so it's Lenehau. And yeah, so she's a professor of applied physics at Harvard University, and she won, I believe, a Nobel Prize for some of her work on trapping and stopping light inside of materials. So this is, some cutting edge research. It's mainstream. But again, I believe there's more applications to this technology with exploiting quantum behaviors. And so the idea is that, you can slow down light inside of a material. And that was sort of what they started with, building, these special materials that could slow down light. And then they eventually built it so they could slow it down to a complete stop. And, it's not the same as, those optical crystals like data storage, but it's useful for storing immediate amounts of light or figuring out how materials work to store light and also trap light and slow and keep it trapped in different ways. So it's certainly I don't have all the answers to how to exactly use this to produce anti-gravity, other than that squeeze states and also polariton condensate seem to be a viable area worth researching as far as producing. Polaritons can produce negative mass, I believe, in some of these experiments, which is what we're looking for in terms of Alcubierre or these other warp drive theories as ways to produce negative mass. And if we can do that through trapping light and pumping tons of light into these materials, then this might be a way to produce enough negative mass or negative energy to build a warp drive.
Awesome. Let me see. Wayne had another question. He was wondering if it applies to phase conjugate mirrors. Sorry, he had trapped light. I think he was asking about trapped light. Would that apply to phase conjugate mirrors? That's something I've never heard of those, by the way. I mean, that was brand new to me. So from what you were saying, you were saying no matter how you orient that mirror, the light always shines back towards the source.
It's like a time polarized. It's like a mirror that's time polarized. So it produces like the exact opposite time signature of the incoming wave that hits it. So again, yeah, it does reflect. That's why when it's going through that fogged glass is sending those photons in every which direction. But that phase conjugate mirror just bounces those photons exactly back the way they came, so that they retrace their path through that fogged glass and actually reconstitute the image again back on the other side. It's kind of similar to what's going on with trapped light, I guess, in a way. I don't know all the exact conditions that they were used in that experiment. It's not exactly the same. It's a little bit different, but again, it is dealing with these quantum optical properties of materials and nonlinear optics. So
yeah. Okay. Who else has questions? Mark, do you have any questions? Mark looks like he might have questions.
Oh, I was just listening to the whole thing. It was pretty impressive. Over 100 slides there. And you had to really powwow through them. What can you actually build in your lab that we can, test or on a 3D printer? What over there can we actually do an experiment with?
Well, I was thinking of getting a laser which can do etching, which wouldn't be too hard to do. If we could hook it up to a 3D printer, we could maybe do laser etching with a 3D printer. It's not
Oh,
too
actually,
far off.
talk about that. My neighbor next door, the machine shop, they're getting a laser, I think a CO2 laser, and they're going to hook it up to a CNC machine that they have sitting on the side to cut metal. I think he said he was going to start with a 30 watt, and then they're going to move up to a 200 watt laser. So all you'd really need is the diagram of what you want, like the G code, and they could print it out for you as soon as they get that laser going. Or maybe we could donate it to them because he already knew, he built that CNC machine. It's the size of like a 4x8 plywood beam. So you could literally print out whatever you want. Just got to have the G code for it.
I like those dielectric mirrors. I think those would be a easy and inexpensive and good place to start with the epoxy thin films that we've already talked about. We can create and cast really flat, really fine epoxy thin films in our laboratory readily, and experiment with different types of etched coatings on those as well, to experiment with trapping light. Also, the idea of one of the sandwich experiments I wanted to try is always the mirror, a dielectric between two mirrors, or the Casimir, force effects experiment. So that there's lots of ideas for coating creating a mirror surface on either side of a dielectric, and also these layered dielectrics, like we said, with the dielectric mirrors. So
also, another thing that you said that was kind of interesting, they took a tokamak reactor and they filled it up with plasma and had it spinning around rapidly. That would be the Podklinov spin experiment, because a plasma, like I told you during the video, is a near superconductor. Some of them I think are superconductors. So if you have them spinning at these really high RPMs, you should be able to see that anti-gravity cancellation effect that Ning Li was talking about in Huntsville, NASA Huntsville.
And it's also a very big scaled up version of those gyroscopes you're playing with too. So it killed two birds with one stone. I think that should definitely be something on our agenda at some point.
If I could jump in really quick, Rob Chambers, and Rob, let me ask Rob to unmute here. He had mentioned, I'm not sure if it's pretty late his time, so I'm not sure. There you go.
Yeah, I'm here. Yeah, it's really just an observation, more than a question, that some of the structures look like Grabenikov's insect wings, the undersides of the insect wings. I don't know if it has any relevance. It's just an observation.
Yes, a lot of those we've found that the Grabenikov's study into scarab beetles and scarab beetle wings. It's lots of interesting things. One thing that has been noted is the shell casing, the actual covering on the top of the wings of the beetle is actually, it's kind of works like about the Biefeld-Brown effect in the B-2 stealth bomber technology, how they charge the leading edge of the wing. Mm-hmm. Well, essentially what happens inside of the beetle's mini electric circuit is that as those folds of the top parts fold off the wings, they actually electrically charge the leading edge of the beetle's wing in a very similar way. And it's based on the way that the nanotechnology and kind of like the way it interacts. It's almost like sliding a balloon across the top of your head, the way it pulls the charge off. And when that wing cover lifts up, it charges the wing, and it creates the anti-charge current. So there is some of that going on actually in the nature, which is cool, because it may be a subtle effect in nature, of course, but nature is utilizing it to the best of its advantage. And of course, we can then find ways to isolate it and scale it up.
If I could jump in really quick also, I wonder if Ron Keaton might have some input on this, because he's done a lot in terms of Grebenikov. Wait, he's doing a timeout. Yeah, wait, yes, no. Yes, oh, okay. He's saying, hold on. I wasn't sure what the hand motion was. I'm trying.
Okay, yeah, am I unmuted?
Yeah, yes, sir.
Okay. Grebenikov, I will mention, I looked in the Grebenikov because beetles being chiral by nature, because they're organic materials, they have to be chiral. But when I looked at it, they have the wing cover. When the wing cover lifts up, it's called triboelectric effect. A triboelectric effect is a triboelectric series. If you type it in, triboelectrics, you have, as the extreme, you have Teflon at one end, which is a fluorocarbon, and you have glass at the other end. They're the extremes. And my understanding of Grebennikov, what provides the levitation is the wing cover itself, that hard wing cover. When you oscillate the wing under it, the reaction between the wing, the combination of vibration and charges against the wing coverlet. It's the wing coverlet that gives the high lift to the beetle. You see what I mean? Also, if you look at Grebennikov, one of the materials he studied was naphthalene, which is hexagons. When I mentioned earlier to Jean-Francois, I mentioned hexagonal structures. And hexagonal structures, why they arise, why they go into monoclinic structures. There is so much here. What I want to do, I'll put a lot of this into an email to Jeremy, because rather than, but like I said, with the elytra beetle, the force is actually on, he called it CSE, cavity structure element. If you type in CSE, because for the longest time, I thought the wing was giving the lift. The wing provides the oscillation and the charge, but the actual cavity is in the wing coverlet itself. That's the hard rigid frame. I think, does that sound right?
No, thanks for filling me in on that. I don't know necessarily. I've never done the experiments myself, but I remember reading a little bit about this. That's all. But I again, you're the expert. Thank you for chiming in.
Well, if you want to see, I have a patent application that the patent office did not like for many reasons. You ever hear of the SAW? I won't bore you with it, but anyhow.
SAW?
SAW stands for Sensitive Application Warning System. You can find, it's been buried on the internet. It's been buried on the patent office. What SAW means is this patent application will never be issued. But the application is still there, and it gets into triboelectric effects, it gets into camphor, and it gets into these material and charges. But that's it. I'll put it all into an email, and so that Grebennikov, naphthalene, hexagons. But your presentation, I would give you a 6-star, but I don't give out 6 stars. Your presentation was a 6-star presentation.
Yeah, it was a wonderful, wonderful presentation. He just ran through so many different amazing things. So, okay, well, let me see. What should we do next? I think that was all of it for our questions. Should we kind of go to an open discussion then, or what would you guys like to do?
I think we should go to open discussion. You're talking about lasers. I just got a new laser in to the lab. It is a. Let me go get it actually.
Okay. Well, while you're doing that, so we will go into open discussion, and let me see. I'm going to step away from the computer for just a moment. I'll put it on mute. So anybody who wants to unmute themselves, guys, just
Thanks so much, guys.
Yeah, and thank you as well, Jeremy. Today was amazing. I was a little nervous because we changed our format, but yeah, absolutely amazing today. Absolutely amazing. So.
The helium neon laser that Jeremiah recommended we pick up for it just gives a very clean beam and dot for experiments to see if there's any deflection. Jeremiah, are you there? Check this out.
Yes, sir, I am. I did not realize that you had that in, but I'm very pleased to see it.
Okay, here it is.
That's awesome. Have you tested the power supply yet?
It all works.
Oh, that's fantastic. Did you notice just how perfectly round that beam is on the wall really far away?
Yeah, it is a very small, tight beam.
So now we can truly test some of those magnet deflection experiments and see what we're looking at. And we have a much better beam profile for doing electromagnetic tests too.
Mm-hmm.
Yeah, it looks good.
It's not a very powerful laser, but that's not really what we're going for. We're just going for the small small dot.
Yeah, you don't actually want high power because it's going to just drown out the camera's CCD when you're trying to actually videotape the thing or photograph how the dot moves if you do have deflection taking place. But with this, you'll be able to see very clearly without totally blasting the camera. If that dot moves at all, you'll see it pixel for pixel.
Yeah, it also has some cool mounting ports, so that would help us mount it to whatever surface.
That is awesome, dude.
All right.
That is awesome.
It also has this little cover at the end, so if you want to shut off the beam without powering it down, you can flip that thing and it shuts off the beam.
Yeah, it's never a bad idea to have a safety shutter. I also do like the giant electromagnet in the background. That's pretty slick.
Yeah, this is the coil we wound. Jeremy came down here and helped with it. It was really an all hands on deck sort of job to get that thing done.
Too bad it's so encased in the framework. I mean, it's nice and strong like that, but you can't quite see the beauty of it. That is if it's beautiful underneath.
I first need to pour the epoxy on it and figure out how we're going to cover it so that the epoxy just doesn't pour straight out.
Oh, I see. I thought it was cast already, but it's not yet, eh?
No, it's not yet cast. I'm still working on like how am I going to do this. There was a suggestion to use like a thin saran wrap, which I think is what I'm going to go with. I need to go pick up saran wrap that would like plastic wrap that would fit this size, and then sort of like shove it in there properly and make sure I get a watertight seal. Because if I mix up everything and then there's a hole and there's a leak, then you kind of just wasted an entire batch of epoxy if I don't fix it in time. So again, it's the kind of job that you really want enough people so that you can fix any errors right away. So this may have to wait a little bit until I have an assistant down here at the lab.
Yeah, no problem. That won't be too tough.
There should be around over 300 turns on this coil, so we'll get some pretty nice impulses.
Yeah, not bad at all. It's definitely going to take a higher voltage to cram into that coil. I like the angle. It's easier to see from the side. But yeah, given the inductance, you're going to have to hit a pretty high voltage into that sucker in order to get enough current through it. That's the, which gauge wire is that?
That's the 13.5 gauge wire.
Perfect. Yeah, that's pretty awesome.
Well, what else do you have going on at your lab?
Well, I am now time testing the dot product disc. I've got it all insulated. The thing came out of the oven. Looks beautiful. Trimmed it up. And so I just charged it up to about 20,000 volts. Let me see, my stopwatch says now, it says 1 hour and 1 minute ago. So after about 4 hours, I will give it a discharge test, see how many microcoulombs of energy were stored in it, and then compare that number to my previous default check where it was instantly charged and discharged. So hopefully it hasn't leaked any charge off, and then we'll know that it's capable of storing that energy for a long period of time, which is pretty much a thumbs up, good to go for assembly of the next Van Dijk static displacement field drive.
Oh, very cool. Oh, we're also being reached out to by a documentary filmmaker who is interested in making a film on anti-gravity. Tom Valone. You might be expecting a phone call from him. Tom, are you there? I don't know if you can hear us, but I told him to reach out to Tom because Tom should be based in Washington, D.C., I believe. Also we have who is that guy who works in Washington as a lobbyist?
Not sure.
There's a UFO lobbyist, integrity research, there's paradigm research. Oh, there's so many of them.
Yeah, I'm familiar with integrity research.
Yeah, there's integrity research is Tom Valone.
Right.
And then there's who's the
back. This isn't your guy, but I'm friends with Robert Kiviat that does the Discovery channel, and he did all the UFO videos, and we go around the US filming and all that. If you want, I could have a chat with him and see if he wants to put a documentary together. what you guys are working on.
This is somebody who's worked for the Discovery Channel and the Science Channel as a executive producer for some of their documentaries, and he's doing it more of a freelance method. But you know, anyone who's interested in doing a documentary, you know, we're all ears, because this isn't just about the technology. If we discover the technology here and then it doesn't go anywhere, it was a complete waste of time. We need to make sure that the masses know about this, and that the technology falls into the right hands and gets taken up to actually building a full-size craft, which is the...
Yeah, but Robert Kiviat's freelance now. He did the Discovery Channel, and he sometimes works with a guy that go around looking about, is the Yeti true or false, or is this true or false? Every now and again, who's a YouTuber, but Robert Kiviat's like heavily involved in like UFO stuff, and but not trying to disprove it. He's like absolute believer and goes around trying to prove it. So I think if you look his name up, Robert Kiviat, you'll see who he is. Might be something or nothing, but it might be worth having a chat with him. But he's very well connected.
Hey, Jeremiah.
Oh yeah, we definitely would be interested. Go ahead, Ziggy.
What's up, sir? I can hear you.
Did you say something about building actual anti-gravity spacecraft?
Let me take a look at you. Yeah, okay, good. Your video isn't on, but even still, your bandwidth is just unfortunately terrible, which is really unfortunate. You asked, are we actually intending to build an anti-gravity spacecraft? Is that what you asked?
Did you say something? I mean, would you like to, or you know? Oh,
I mean, if we could, we would. If we could build one, if we knew enough to build one now, we would already be constructing one as we speak. So, absolutely.
So, and you know what? I have actually a very easy design for anti-gravity craft. But would you consider supplying the cables from the ground first?
Oh, I mean, we don't mind the test thing if it's tethered. If it requires external power because we can't put power on board for some particular reason, although you'll find it's actually a lot easier to put power on board than you might think.
Yeah. Okay.
Yeah.
So listen.
Yeah, no problem.
So
no problem being tethered. If it floats, it floats, right, Ziggy?
That's right. That's right. So you know, if you're interested, I have a very simple design, but of course, this is based on the assumption that our experiment will produce some decent results, right?
Right. So first we test your baby space drive. And I'm really looking forward to that. I really want to see what happens when we actually do stick something like 200,000 volts in the tiny amount of space that we're intending to stick that power. I've been thinking about how I actually want to get that voltage in there and then extract out the probe, because obviously, I don't want to rotate the power supply with this entire thing. That seems to be ridiculous. So I'm thinking that there's probably going to be a long tube-like entry port that runs along the outside of the cylinder, that sort of this long wire with a exposed end goes into, and that way we can pull off the electrified probe and leave the entire thing charged, but the distance of ionization path is too long for it to effectively discharge. Either way, we'll figure it out, but it's a lot of voltage in a really tiny area, and with a field that's effectively up to 65,000 Gauss, well, yeah, it should be fun. If that doesn't prove the principle, I don't know.
I think it should be sufficient to produce easily observable results. Hey, Jeremiah, I'm totally, I'm totally convinced that it will work. But how big would you like to make this first anti-gravity spacecraft?
Well, honestly, my personal preference has always been to develop a small personal pod-like craft. Just a one-seater, you know. That way, if it goes completely catastrophically wrong, only one person has to go down with the craft. But anyways, that's a proof of concept principle, and we've all been promised flying cars, so of course I want one for myself, and I'd start with building that.
Oh, I see. So you would go immediately for a manned version as opposed to unmanned, right?
Yeah, I'd want to build something small that the risk is only limited to one person at a time.
But we could start from just a craft smaller without the person.
Oh, I'd be down to build a drone. I'd be very down to build a drone, a radio system. Absolutely. That would be sort of the ultimate proof of concept. Heck, if we had that, we could just go do a TED Talk about it.
Yeah.
Notify the world. Hey, look at this.
Before some. Yeah, exactly. The TED Talk would be fantastic with the drone. And and before somebody risks the health, we test the drone first, right?
Right, it's exactly all about the, hey, it actually works. It exists, right? It either works or it doesn't.
Cheaper and easier, right? Yes. So, from my side, if we have at least 4,000 RPM and we have this 200 kilovolts, there will be easily observable movement, honestly, I have no doubt. Actually, be stronger than we expect.
Yeah, this will be really interesting. With all the laser beam experiments too, we'll get to try that out.
So I just want to.
So when do you think we could give it a try? No rush, but just ask me.
Just to kind of give you a time frame. So the magnets are in. I've been playing around with bearings that I think I can trust. I'm trying to locate an all stainless steel low magnetic bearing, something that I can put some better lubricant in or something like that, where it's not going to be extremely screwed with by the fact that it's in directly one of the poles of an extraordinarily strong magnetic field. So that would be the goal, is to find a bearing that is capable of operating under the flux intensity of this magnet that it's being attached to, and get those bearings as close to the rotor as possible. So once we get that set, it's just a matter of rotating it, hooking up a motor either directly or via a belt drive to that thing, and then we can do the basic magnet test, the unenergized non-capacitor magnet test, while aligning it parallel with the surface of Earth, and then measuring its mass on a small type of either pendulum system or a hanging wire suspension system.
Mm-hmm.
So I just wanted to let everyone know. Just a second, Ziggy. So everyone knows, for future podcasts, I learned a lot about podcasting, and like the best microphone on the market for the price right now is probably the Shure MV7. So if you are like Ziggy and you need to upgrade your audio setup so that we can hear you without sounding like you're broadcasting from the UFO itself, this would be we can just hear you, man. It sounds like you're like blipping in and out. It sounds like you're broadcasting from the Zeta Reticuli star system or something.
If I could jump in really quick, also, you'd probably want to
gravitational waves. There's just too many gravitational waves right now.
Yeah.
I just got on my UFO.
I posted that microphone in the chat so that people who want to do future conferences will know that's a good microphone. That's
let me also post the speedtest.net. I think that's also really valuable.
Yeah, because sometimes you can sometimes you need to upgrade your bandwidth or your cable or internet service so that it works better for upload and streaming. That might be an issue too. It might just be dropping periodically because of that. But it does this. I view these things as historic, what we're doing here. So I just want people in future generations, when they have to go back and do the research on how anti-gravity became a real thing, because people believed in it and didn't give up on it, that they are watching these. And I don't want, the worst thing we want is bad audio on the historical record. So.
Yeah. If I could jump in terms of the speed test, and because I do a lot of work online, the way, in fact, here, let me mute you out for just a sec, Ziggy. I'll bring you back in. sorry, he's getting some background noise. So it could be the way things are configured as well. Some of the common things to look for, if you go to speedtest.net, if you're below 30 megabits per second, you may experience some issues. Usually your upload speed is significantly lower than your download. I would say that anything below about 45 used to be the standard, right? And this is almost 10 years ago. That was the standard for cable modem. Everybody kind of took it up to that. Comcast and Cox and all the big ones were about 45 megabits per second. Anything below 30, you may experience some issues with video conferencing and stuff like that. So again, do speedtest.net. You may also look at microphones. Not all microphones are the same, as Jeremy has kind of pointed out. There's actually, when it comes to computer mics, there's actually more going on behind the scenes. For instance, if my video is up, I don't know if you guys can see mine. I'm using the Blue Yeti. This is the older version. They still make these. These are really popular. The hardware for it is, I believe, 8-bit instead of 16-bit, or 16 instead of 32, or something like that. Also, the kilohertz for some of them may not align with what your computer wants. You can adjust all of that stuff in the settings on your computer, but most of us don't want to. It's a nightmare to do. So usually spending a little bit more for a good mic, is better. I've had good luck with the Blue Series.
The Shure MV7 is about $250, and then but really the preamp is where you want to spend the money, if you want to spend the money, because the preamp's what you're plugging that mic into, and it has to have I believe phantom power to run a condenser mic. So that's like, it's an investment, but if you're going to be doing a lot of these, and believe me, I went to Guitar Center and they're sold out of these things now because of all the people with COVID and everything going on. There's so many people starting up podcasts and buying these to do this. So it's actually a shortage right now, pretty much. But they've gotten over that now. There was a shortage, I will say. Actually, correct that. There was a shortage about a month or two ago, but they've yes. But anyways, that's a side note, so people can know about that.
Well, no, Jeremy, I think this is really valuable info, and I think a lot of us overlooked that. Another thing, this is an area I've noticed some folks have trouble with, and they don't always realize. Actually, there's two things. One of them is you want to have a good Wi-Fi router. You may have one that's built into your cable modem. If there is, you want to make sure that you have a password on it so people aren't leeching off you. Let me see, I use Netgear wireless routers, Wi-Fi routers, and I actually use a separate Wi-Fi router and cable modem because the ones that come through modem usually aren't that good. Wi-Fi is a real issue for some folks because the signals bounce off the metal in their house frame or things like that. So Wi-Fi is unpredictable. On my PC, I actually use an Ethernet cable still. I'm kind of old school, but you still get higher bandwidth, better quality, and you don't get dropouts. So that's one thing. Another thing is if you do have a separate Wi-Fi router and cable modem, you want to make sure that you get those probably about 5 to 6 feet apart. This is something that's undocumented, but when those are too close together, they interfere with each other. Your Wi-Fi router can actually knock out your cable modem.
Like something to include that not wireless but wired connection in a router is preferred because it will give you a faster connection, wired.
Yeah, wired directly rather than go through a Wi-Fi always, if you're on a laptop or yeah. So these tips are important, man, because it took me a while to learn these things, and it's really all about experience. And you'll go through a whole bunch of different products before you'll find one that actually is the right price and stuff. And you'll go through a lot of reviews and stuff. It's hard to get that information sorted out. So it's kind of good to learn from the pros, which is what I did to find that MV7 mic. After I already bought this $400 AKG, I find out there's a superior podcast microphone that's made just for this, and it would have been $150 cheaper. Well, hindsight, like a guy in the chat said he already bought a Audio Technica mic, and so yeah.
We actually spent a whole afternoon getting a wire connection here into the lab for the live stream. So actually had to drill holes through the wall, and Jeremy and Jeremiah were helping me out to put a wire in directly from the modem because we're having Wi-Fi problems. So we're not going to have any of those problems again when we're doing live streams.
Well, you know, one thing to think about is how much time you spend online, right? And I don't want to be that guy, but my grandfather always said, spend the money on the things that you use, right? And the more you use it, the more it's worth spending on it. So his thing was, don't waste money on stuff that you're never going to use, that goes in a drawer that you forget you have. And so when it comes to stuff like computer equipment, I always try and keep that in mind. Is, you know, in my case, I usually don't do the gold standard. I usually try and find the silver standard where you get that best price value comparison, you know. But I know a lot of other folks who, you know, it's one thing to cut corners, but sometimes with computer stuff, if you cut too many corners, then you end up in kind of a world of hurt, and it ends up wasting more time than your time is worth, you know.
But yeah, and then you need the headphones as well, because it will pick up these condenser mics are really sensitive, so it helps to have headphones so they don't pick up ambient sound. And yeah, other than that, sound. How about sound for acoustic levitation? Anyone done any experiments with acoustic levitators? I know some guy some guy I met built one. He showed me all the pictures of the thing he built with to do acoustic levitation. I always thought that was pretty cool.
Yeah, Jeremy, I actually did putz around with acoustic levitators. This is what I ended up doing, is filling this transducer here. It's a 50 watt transducer being ran on a 100 watt board. And so you can see I filled the center with lead, just sort of create a flat plane. And then this you can resonate against a flat piece of glass, metal, or anything else that has a nice even parallel surface. And if you space it correctly, you'll build up standing waves, and you can pick up little pieces of foam or, you know, glass or sand or whatever, and stick it in those nodes and antinodes, and you'll be able to trap them right there, and they'll sort of buzz up and down because the regulation of this board is garbage. But if it was nice and easy, they'd hold themselves perfectly still and they'll levitate. You can stick almost anything in there that's light enough, and it'll grab it.
Nice. That's pretty cool.
You know, we want to use that to drive this, you know, this piece of metallic glass.
Oh yeah, we got to etch that with some shapes, and then see if we can't trap sound and light together.
Have you guys?
Go ahead.
Have you heard of this new app called Clubhouse? It's basically just audio only rooms where people talk about different topics. Has very good fidelity audio. It's like a new social media app, and nothing is recorded, so you can just join these different chat rooms. And I was in there the other night listening to people talking about quantum computing, and they have a whole bunch of rooms on space. They got NASA astronauts there, people who are working on the Mars rover, like really interesting people that are just sharing their story, and everyone's listening. And you can get up on the podium and, you know, share your thoughts as well. It's a really cool app that just started. I know, Jeremiah, you thought you were interested in it as well.
Yeah, I am interested in it. I wouldn't say that nothing's recorded, since no such agency, I'm sure, records every conversation there. But regardless of that, it does sound like a great chance to bounce ideas off of other actually alive human beings, which is usually a good idea when you're trying to get, you know, somebody to sort of BS check you to see if you're totally out there.
Yeah, so I was thinking of starting a channel on anti-gravity or alternative propulsion, and see if we can get this out to a more general crowd. I started a little room. I got like 100 people in it at one point. Then I was trying to explain dynamic nuclear orientation, and I got a couple people on the stage that kept on trying to get me to simplify stuff a little bit more and more. You know, it kind of like puts you in a position of talking to the average, you know, Joe the plumber. You got to explain it to him too. You know?
Right. We all need to get good at doing that, because ultimately they're the people that have to sort of take over this stuff, and they've got to build the craft and all of that.
Yeah. Well, hopefully we'll be the ones setting the parameters on the machine, and they'll push the button, you know, put the metal in.
Well, yeah, space isn't going to mine itself, and the craft aren't going to build themselves, but somebody's got to design them first. And, you know, we're trying.
Well, I'm really excited by what we're doing with YouTube. I mean, Jeremy is the big dog in the house in terms of YouTube, right? Every time we do one of these sessions, he gets thousands of viewers. And then I'm also putting them up on American Anti-Gravity and the new APEC channel. And we're picking up, hundreds more per each session. But the thing that's exciting to me also is it's out there in multiple places for posterity, and just the ideas that we're generating, we're producing and documenting, right? And one of the experiences that I've had with American Anti-Gravity, and I know Jeremy's probably had the same because he's been doing videos for over 10 years, is that people will see this material and put it to use, and it may not come directly back to you for years, maybe even decades, but it's out there, and it's changing minds, and it's inspiring people. For me, that's exciting. It's just getting the material out there, and although it can be a little scary because it goes out there and you see the views, but you may not get feedback, right?
Sean just mentioned if we keep this up, we might get sponsors, which would be exciting. I noticed today we had somebody from the media was in the crowd listening quietly. I think it was, I posted it in the Falcon Space chat, his name, but he has a media channel related to, UFOs and the paranormal kind of stuff. But we're getting out there, and hopefully we'll have more mainstream media coming in here as well and reporting on us and taking this story mainstream. I know Jeremy Reese was just on Tim Pool, which is as mainstream as we got so far. And of course we had Nick Pope, and he did a shout out for us when he was on the Ancient Aliens podcast the other night. I slipped him a note in the questions to make sure he mentioned us. So yeah, we're definitely getting out there, and hopefully we'll get some sponsors one day, and we'll be able to bring it all together.
Wonderful. Well, guys, should we wrap things up for this evening?
Yeah, I just want to add one more thing before we close up. And they said that, back when you started doing this in 2002, I think it was true that we didn't see anything come around. It took like 10 years to really a decade to get a lot of those early ideas out there with Pod Klitnov and John Hutchison and some of these other guys, Searle and some of those other guys, to kind of almost like a way I look at it is breaking the ice in some ways for these other future experiments to come along. But that's kind of how it all started. But I think like what we're doing with this conference, it's already, like I said, it's already taking off on and taking on a mind of its own. The amount of people I've gotten in my inbox, I've been writing emails and busy responding to emails for the past 3 days since I was on that podcast on Monday, and it's been insane with the amount of outreach that we've had. I think that those days of waiting, years for results is over. I think that people are hungry and ready for this now more than they ever were, and it's going to take off in the next just couple of months. I've been already in talks with a bunch of different people who've contacted me. I have a bunch of ideas flowing right now because since I got back from Tim Pool's, they got a stream house. This is like a big thing that's going on now. It's taking over a lot of these gamers. They'll all get together and get a house, and they live together in the same house, and they all stream from that house and do games together. They go on each other's streams. They support, the other people's streams independently, and that's kind of like what Tim has going on. But so I learned a lot from him as far as how to edit video, get a team going to edit video and pump out content. And we kind of have a similar idea, but it's based around this anti-gravity research stuff again. And I think that would be it. There's a lot of TV shows and people with big money that would invest in something like this, a stream house that we could run for like the MTV's The Real World, but for anti-gravity, or like. And I was even thinking, we were running ideas just in a brainstorming session. We could make this like Survivor and have 12 people on the island, and one gets voted off every month, where we bring a new guy on to try to add to the team.
We kind of have the lab house already set up. It's a 5-bedroom house, literally 5-minute walk from the lab. And I'm actually busy building some IKEA furniture that we got. that everyone can sleep on it, something other than air mattresses.
So now we need to wire that place up with like video cameras. I want, we gotta have our privacy, but you know, I don't know. I got some ideas, you know, like you get the ideas flowing, man. That would be awesome. Keep going with that. Okay, Clay Moore gave me a super chat. Imagine an empty inverted spool of thread. When the full end falls out, the thread is voltage. Stick a rope in and it kinks and flops out. Ultra high amperage, very low voltage. Yeah, it's similar to that idea, I guess. You could use a string as analogy and like the windings of the wires. In a way, pumping up the voltage. But it's all about the ratios is really what it is in transformers.
Well, guys, why don't we close things up for this evening? And I mean, I can leave the conference going if you want, but
no worries, man. That was good. We killed it, and I don't want to keep it on too much longer. I want people to check out that and again, you can go to American Anti-Gravity Events to stay tuned for future APEC conferences and events. falconspace.org and alienscientist.com.
Altpropulsion.com is
and that's our official website now.
All right. I'll type it in the chat right now.
Altpropulsion.com.
Anyone who wants to sign up for the Zoom links should sign up over there. And I think we should change the blue background back to the one it was before.
Yeah. Okay. Let me take a look at that next week. I'm juggling, as you know. I hit the blue and I said, "Oh, I love that. I have to keep it." But if it's driving you nuts, I can change it back.
All right, you can go ahead and wrap it up right there, then, Tim. That's
okay.
Big round of applause.
Big round of applause. Thank you, everyone. Who's left anyway? Did everyone go to sleep?